Good morning, good afternoon, good evening, everyone. We are here for the 6th module of this SAMOSAFER online school on MSR technology. The subject of today's module is operation and control of molten salt reactors. We have a very dense schedule as usual, so we are going to have a first basic lecture followed by an interactive part. And in the last hour from 4 to 5, we will have a specific webinar that has its own dedicated link. Therefore, we'll need to close this connection and open the new one with a focus on the differences among different reactor designs. Now, so we can start now with the introductory lecture on operation and control of molten salt reactors with the contribution of Professor Elsa Merle, that all of you should know already since she was already giving us a contribution in the previous module. She will discuss MSR operation and control together with Axel Loro from the same institution, from CNRS, and with a small contribution also from Stefano Lorenzi from Politecnico di Milano, and then they will also be interacting in the following part of the lecture. So I leave the floor to Elsa and Axel.
Thank you very much, Sandra. So hello everybody, we are very happy with Axel to present you today some elements on the operation and control of molten salt reactor with an application on the concept of molten salt fast reactor on which we are working. So next slide, please. So as I mentioned during the previous module, and as you already know, MSR molten salt reactor are one of the 6 concepts selected in the frame of the Generation 4 in an international forum, as you can see here. And it's the only reactor with no solid fuel. It means it's the only reactor with a liquid fuel, which gives some characteristic very specific to take into account when defining how to operate or how to control the reactor. So next slide, please. So I will just remind you of one slide that I presented last time during module 5. As you know, the idea is to define innovative reactor when we take into account what we want to do with the reactor. So we just have to define the objective of the reactor and then to identify the best concept available to fulfill this objective. So as I already mentioned, there are many objectives for a nuclear reactor and associated related specifications. It depends on what you want to do with the reactor. Once you have defined one objective for the reactor, then you have to select a reactor concept with qualities coherent with the specification and to adapt the concept to what you want to do with the reactor through studies, optimization, experiments, etc. And finally, when the most precious thing when you define an innovative reactor is to have reactors that allow to have new options and more flexibility in terms of safety, as will be presented in the next module, in terms of design, as I presented last time, and in terms of operation that we will present today with Axel, and for example, controllability and load following. So just click, thanks. Okay, so the idea is to continue the presentation of the flexibility offered by MSR. The main characteristic of molten salt reactor is their flexibility in all domains that are of interest to have a very useful reactor that you can adapt to many objectives. And today the idea will be to illustrate the controllability of the reactor through, for example, load following and how do we start the reactor. And when we consider this characteristic of MSR, click again, please. We have all the families that I introduced last time of MSR. So for all these families, and for each MSR family, we have to define how we control the reactor, how we operate the reactor. And today we will focus on the molten salt fast reactor to illustrate how we define this with a reactor, for example, with no control rods. So can you please, next slide. So the molten salt fast reactor concept that you can see here with all these systems is a reactor using a fuel under a liquid form, and the fuel is also used as coolant. It means that the fuel is circulating between the core and the heat exchangers in the what we call the fuel circuit, because the primary circuit is not a correct name. And you can see that we have, since there is circulation of fuel motion, we have also a circulation of the delayed neutrons. And a part of delayed neutrons will be emitted out of the critical region, which has an impact, as I think you already see it in neutronics and maybe in thermohydraulics module, as an impact of the operation of the reactor. For this MSFR reactor, we have excellent feedback coefficient, -1, both density and Doppler effect. And the total feedback coefficient is of around -6 ppm per degree for the reference MSFR concept, the breeder reactor in the thorium fuel cycle, with half of the effect coming from density and half of the effect from the Doppler. And it's a lithium fluoride salt. As you can see on the left part of the slide, we have a fast neutron spectrum. So you have in blue the fast spectrum of the MSFR, and in red the spectrum of a sodium fast reactor. And you can see that it's quite equivalent, except for the sodium capture cross section in red, and except for some inelastic cross section in blue. But we have a fast spectrum. It means that there is no quick neutron poisoning by fission product. Also, as we will detail when we see maybe more precisely the fuel circuit, there is no control rod in the reactor. So the challenge will be to explain you how we drive the reactor, how we do load following with no control rod. And also, as for sodium fast reactor, we have no high pressure in the reactor. Please click. Of course, we don't only have one fuel circuit when we have to take into account the operation of the reactor. We have also in yellow the intermediate circuits, and containing other molten salts with no radioactive matter, and of course, so it's high temperature and low pressure, and also by click, we have finally the heat conversion circuits. In red on the figure, with a high thermal efficiency, and of course the high load following capacities, which are not specific to nuclear electricity generation, so which have to be investigated. And the idea is to determine what is the maximum power range that we can reach with this reactor. So next slide, please. So for it's possible to have next slide. Oh, okay, sorry. Yes, there is two additional systems. There are the draining and storage tank, and also processing units, but we will not speak on this element today. So to continue with the specification of the molten salt fast reactor, the innovative features of such a reactor compared to solid fuel reactors are the elimination of most of accident initiators. For example, we have no control rod, we have no rod ejection. And also we have worked on this part on the initiators. We have reduced the initiators, leading to a first accident to a worse second one. And all safety coefficients are excellent, as you will see in the next module on safety. We have a large flexibility in the design and operation of the reactor in terms of fuel composition, but today we will see in terms of reactor operation and power level. We can do load following with the reactor, even with no control rod, and we can have reactor from small modular reactor to large size reactor. You can see a view of the fuel circuit of the reactor at the bottom part with a small video, where the fission are occurring in the center of the core of the active zone, as we said, and the fuel is entering at the bottom of the core, is heating in the core, and is extracted by the pump to be cooled down in the heat exchangers. And classically, one turn of the fuel in the circuit takes about 4 seconds, so it's quite fast. And the system is quite small. The core is 2.3 meters by 2.3 meters for the large power version of the MSFR. As you can deduce, there is no classical fuel fabrication, no fabrication of cladding, assembly, leading to a cost reduction, but also it's easy to add actinides, burn them in the reactor, and of course this will impact the reactor operation. So there are many PhD theses at CNRS, and also I had one in Polito, working on this characteristic of design and safety related to the molten salt fast reactor. So next slide, please. Oh, yes. And as I mentioned last time, during module 5, during module 5, we work on the design definition of the core of the draining system. Then I promise you that today we will work on the development of simulation tool dedicated to molten salt fast reactor, and to the definition of the more normal operation procedures. We are going to that now. And in the next module, in the final module, in the 7th module, you will have an evaluation ID on safety evaluation and safety approach. So now we'll focus on normal operation procedures and development of associated simulation tools. And maybe I will explain now what means normal operation procedures and normal operation states. So next slide, please. So before defining operation procedure, we have to know what are the operation states of the reactor. So to identify a normal operation state, the idea is to identify the location of the fuel salt in the circuit at each part of the reactor operation, and how the safety functions are ensured. Safety functions, it's reactivity control, heat evacuation, and confinement. And then we have to define one normal operational state each time for each evolution of the heat removal strategy, the transition of the salt from one place to another place, and for each confinement strategy. For example, when we open the fuel circuit, or when or for the circuit that are connected to the fuel circuit in case of bypass. So we have one operational state or substate for each location of the salt, leading to one strategy of heat removal or confinement. You can see on the right the drawings of the MSFR system with in the center part in yellow the core, so what we call the fuel circuit. Then on the right in green the intermediate circuit, on the right a part in purple of the heat conversion circuit. And you see that there are many other circuits in pink, in blue. What are there? It's drawings of how do we extract heat during reactor operation, and also when we stop the reactor or when we lost the traditional heat extraction. So it's additional heat extraction devices that will be used to operate the reactor in any case of whatever happens in the reactor. So you can see that we define the heat removal strategy for each place on each state of the reactor. And related to this heat removal strategy, we have identified normal operational state, which are reactor in power, normal shutdown, maintenance shutdown, maintenance cold shutdown, and startup of the reactor. And now I will illustrate two of them that we will continue to see during this lecture: reactor in power and startup of the reactor. So startup of the reactor, I will come back to this by simulations, but first we have to preheat the reactor because the reactor casing has to be closed, and we have to put everything at a higher temperature compared to normal, to what we have on Earth. So we will use the intermediate circuit to preheat everything. Then we will, once the circuits are preheated, we will load the intermediate fluid. So we'll melt the intermediate salt, and then we'll charge the intermediate circuits. Then we'll put it in circulation, and the intermediate fluid is circulating in the walls of the reactor. So by circulating the intermediate fluid, we can heat the walls of the reactor and then the fuel circuit. Then we will melt the fuel in a fuel storage area, and then by batch we will add the fuel in the reactor. So we will fill in the reactor. And during the reactor fill-in, we will have a reactivity measurement to be sure that the reactor is not critical before being full. And then we will have to adjust maybe fuel composition once the loading is complete to have the correct temperature, criticality temperature corresponding to the normal temperature operation of the reactor. And then, of course, but we will start. We will have to control the fission by checking all the devices and the controls, etc. And of course, the fine tuning of the criticality temperature that can take days. And finally, the reactor goes to the reactor in standby state, leading to the next place, the next state, that is reactor in power. So click, please. Thank you. So reactor in power. We have first reactor in standby. The core is critical. We have to check it. we extract only decay heat in the heat exchangers. And then, as you see, the heat exchanger, so in this place, we use the heat exchangers in orange on the figure in the right. So it means the BHX and AHX. So it's additional exchanger just to extract decay heat. And then the salt is put in circulation. We start the, let's say, heat steam generator or equivalent, which are in red on the figure, the CHX. They are working, they are connected to the turbine, and then we have nominal power production. We can define another substate, which is maybe power production at a reduced level. So it means when we are doing load following, we can define another additional substate, which is not down here, because we think that maybe if we operate at a lower power, maybe some of the CHX will not be used. Maybe only some of them will be used. So we can still refine, it's under definition, and we will refine also by adding substates if necessary. So that's all what I wanted to say on MSFR operational states. And then there is one thing to understand: what do we need to define the procedure corresponding to the operational states? So to move from one operational state to another operational state. And as you can see from the beginning of the lecture, I am discussing on the system level. It means we have all the circuits interacting together. We need for these system codes, or if you prefer, power plant simulators. And also, as you can see, I also mentioned the fuel circuit. It means what happens in the core when we are moving from one operational state to another one, to stay in the safety rules, to keep the safety level high. And then we need also to know exactly what happened in the core, in the fuel circuit, by precise 3D transient calculation with simulation tool dedicated on coupling physics. For example, neutronics, thermohydraulics, coupling. And then you see that we have two levels required: system level, core scale, and we need two kinds of tools to simulate and to define the operation and the control of the reactor. So, Axel?
Okay. So before explaining how to model those and how to go on those different operation states, the idea here is to explain what are the different codes we are going to use for this. For the two first codes, two system codes, LICOR and the Modelica simulator, they will be used in the interactive part of the webinar. And the last one is a 3D code called Tfm Open Form. For the first one, LICOR, please, if you want to access to the code, so it's free, just send an email to me and also Elsa, and precising your institution, and if you want to be added in the mailing list for future. So the objective of here is to understand how these codes are working, and you can find detail in the literature if you want, of course. So for the system codes, usually it's possible to split the system into different parts. The core, which is very specific with molten salt, with circulating fuel, and also all the parts on the right here with the intermediate circuit and the heat conversion circuit. In the LICOR modeling, there is a split between the core part and the intermediate plus energy conversion circuit, which is modeled with an ALICE module developed by Coris. So first, how is working as a neutronic part of this kind of simulator? So we are using usually point kinetic. So what's point kinetic in a nutshell? So quite quickly, but explaining how this is working. So let's say that we have a fraction of time dt and a lifetime for the neutron, which is L. The fraction of neutrons that are going to disappear is dt over L. And for all of these neutrons, the absorption will be the amount of neutron n times this fraction. And each time a neutron is absorbed, they are going to produce k effective new neutrons. So beta times k, with beta as a fraction of delay neutron precursors, 1 minus beta new prompt neutrons. In the same time, we have the decay of the precursors, lambda with the decay rate. So here is the decay term of the precursors, and one decay is providing to the system one new decay neutron. delay neutron, sorry. It's not decay here, but delayed, sorry. And at the end, the point kinetic equation is just balance equation of these terms, with here the absorption term. I don't know if you can see my pointer. Yes? Yeah, okay. So here we have the absorption term. Here we have the probe neutron production, the delay neutron production here, and the precursor decay seek term and source term here. And finally, if we shuffle those equations, we obtain the classic point kinetic equations. For fixed fuel, a classic improvement is to say that, okay, decaying precursor is not giving one classic neutron, but a delay neutron, which is not equivalent. And the ratio, this factor is correct. This correction is in the beta effective, the effective fractional delay neutron. But for a circulating fuel reactor, it's a bit tricky because we cannot estimate this effective weighting from the precursor creation, because it will depend on where is the precursor going to decay. So for this, we need the spatial tracking of the precursors and a local weighting when the precursors of delay neutron are going to decay to see the impact on the chain reaction. So for this, for LICOR, we are using multiple 1D fuel motion inside pipes. So here we have the core, the pipe, the heat exchangers with a linear motion inside. A cost-based cell function for the neutronics. So as for any point kinetic approach, we split the neutron population and the neutron distribution, and we have the equation we showed just before. So here's the variation of the neutron population with the reactivity, the precursor term with beta, which is a source term here for the precursor family, and the decay term, which is a source term for the neutrons. And that's all we need for this neutron approach. And we can see that this is important to see this LICOR, which is IPK here. It's important to see some oscillations due to the fuel motion. But if we are only looking to the long-term distribution, the long-term behavior of the reactor, and improved point kinetic, such as done by David Le Carpentier a few years ago, is able to reproduce a molten salt reactor without those oscillations. So it's possible to do it in a more classic way, if needed. And at the end, the LICOR code is taking into account what's happening in the core, and it's coupled to the ALICE simulator developed by Coris. And the idea, as you can see here, is that we can use all the classical modeling of the intermediate and more specifically to the heat conversion circuit, especially, for example, for supercritical CO2 turbines. And now we'll switch to the Modelica modeling. So Stefano, I don't know if you can speak.
Yeah,
yes, you can.
Thank you. So the second, let's say, power plant simulator that will show you this day will be a Modelica based one. So Modelica, it's a modeling language which is object oriented. So this means that, as you can see on the right side, if you want to model a turbine or a simple pipe, you will have the object correspondent which corresponds to this object, and then you will have the corresponding equation related to the dynamic behavior of this object. So usually Modelica, it's an open source language, so you can go to the website and download this language, and usually these components are collected in some libraries that are dedicated to a specific topic, to a specific modeling purpose. And the Modelica language is, let's say, based on a 1D description with a finite volume discretization. On the bottom part of the slide, you can see the power plant simulator that has been developed in the SAMOSAFER project, with the primary loop, the intermediate loop, and the power conversion loop. Next slide, please. So actually what you find in these boxes are, let's say, several components that are connected all together in order to, let's say, to have, let's say, this physical representation of your system. So you have on the left side the primary loop with the core and the heat exchanger. Then you have the intermediate loop and the heat exchanger, the intermediate heat exchanger, and then the power conversion loop. Next slide, please. During the previous project, we used this simulator in order to, let's say, test what Elsa was discussing some minutes ago. So the capability of the molten salt fast reactor to, let's say, to respond to a load demand reduction from, let's say, 100% to 50% without the need of a control rod. And you can see in the first two figures the mechanical power and the thermal power of the reactor, which are constantly reduced in the different step, and then also all the other, let's say, variables: the fuel temperature, the intermediate salt temperature, and the gas temperature. So thanks to this kind of, let's say, power plant simulators, you can really have let's say, a look on what happens in all the different components of your system, not just on the fuel circuit, but let's say from the neutron in the core to the electron in the grid. But then I will let's say talk more in the interactive part. So I give the floor to Axel for the continuation of the presentation.
Thank you. And the last one is coupling, a 3D coupling between Tfm and Open Form, which is an open source code. So the CFD take into account the thermal hydraulics. The neutronics is taken into account by the Tfm model. The Tfm model is some kind of generation of green function from neutron Monte Carlo calculation in order to get the probability to go from one position to another, and also in how much time you need to go from here to here in the reactor, for example. And from this, it's possible to take all the neutron kinetic inside the open form code, and then with some specific kind of numerical scheme to couple the neutronics and the thermal hydraulics, because they have different time scales. It's possible to couple everything in a single tool. So that's something very useful to model the code, to model this kind of studies, this kind of reactor. Sorry. And just to note, there is some future development to couple this TFM also inside star CCM instead of open form, to have something which is a bit more user-friendly. So here, I think it's back to Elsa or I. No, from I. So here we have the molten salt characteristics, which is a liquid fuel, no control rod, and the idea is to see how we can model the normal operation, and for example, something very classic, load following. And the idea is to be able to do it without control rods. So the idea is to use only the neutronic feedbacks, and thanks to those feedbacks, if we stop the heat extractions spontaneously, the core is going to decrease the power, but the temperature are going to change. Then the idea will be to change and to control the fuel salt separation speed to maintain the temperature variation inside the fuel loop. To do the same also on the intermediate circuits. It will be also possible to optimize this in order to smooth the transition during the load following, to avoid to have some strong variation which can be avoided if possible. More important also, if you just do those two fluid circulation speed adjustments, there will be a shift on the average temperature on the intermediate circuit. And to avoid this, it's possible to use a bypass. And then we have one more freedom available. And then we can adjust this average temperature thanks to this bypass. If necessary, it's also possible to adjust the temperature in the core by changing the proportion of bubbles inside the core. For example, with 3% of bubbles, it's possible to decrease the temperature by 100 degrees, so that's nice. However, it's an accident initiator. So if it's possible to avoid this initiator, that's a very good thing. So if we can avoid to have bubbles in the critical region, especially for the fuel treatment, because it's not necessarily mandatory, it's something to be investigated. For example, putting it inside the expansion vessel, it would be more interesting to avoid to put those bubbles in the core to avoid accident initiators for the safety. For this, precise transient calculation at the core scale are performed to develop and validate those simulation tools. And also, plant simulators are necessary in order to see what's happening up to the heat conversion circuit. And there is a PhD thesis starting on this topic at CA very recently. So here we can see the results for the core side. We can see here during this transient from 1 to 3 gigawatt in 10 seconds. So that's something very fast. It's not necessary to be that fast. The idea is just to illustrate that the constraints are not going to come from the core, but from the intermediate and the conversion circuit. So the power, extracted power, is going to increase very quickly, and spontaneously the produced power is increasing thanks to the feedbacks. You can see here the reactivity, which is increasing and then stabilizing. Thanks to the adjustment on the fuel circulation on the pump's speed, the variation of temperature inside the core is constant during the transient. So even if we are increasing the power, the temperature on the walls are more or less the same. You can see here the power inside the core, which is increasing, and on the left, the fuel temperature, which is more or less constant in distribution. And then we switch to the filling procedure for the reactor with Elsa.
Yes. So to finish, we will present another operational state of the reactor. After load following, we will study the impact of the characteristic of molten salt reactor on how do we start the reactor. It means both the approach to criticality and then the divergence of the reactor. We have two steps, and we have to do this without control rules again. So I remind you, we have a liquid circulating fuel reactor. There are no control rules, and then we have to adapt what is done currently, for example, in PWR, cannot be done directly in the molten salt reactor. So as I already detailed to start the reactor for the startup procedure, I will start again by explaining maybe in some much more details what can be done. Of course, nothing is fixed. And of course, also, we present just before detailing the startup procedure. What we explained today are the state of the art of the research at the current date, but we are working in SAMOSAFER to define more precisely the control of the reactor, as mentioned by Stefano. And also, once we have defined operational states and operational procedures, it means operational states, and then how to go from one operational state to another one, while keeping the reactor safe. We will also have to work then after on what happens when we don't stay in the correct operational state. What about deviation from the operational state? And when is the situation not safe anymore? It means what do we reach a state of incident or accident? Or more precisely, how can you prevent the reactor from going from an operational state to a non-correct state? And then we have to identify deviation. We have to do control, instrumentation, etc. to identify deviation. Of course, we will also have to define procedures to come back from a non-safe state to a normal operational state. All this is not done. It's why we don't present this today. And if you are interested to work on MSR, so there are a lot of work to do on that. So today I will just on the startup procedure explain what we want to do correctly and maybe some first ideas on what can happen that we don't want to see, or also what can go wrong when we start the reactor. And we will illustrate this to give you an idea on the researches we are doing right now. So to start a reactor, we have to put the reactor in the critical state. And then once it's critical, we would like it to produce power. So first, the approach to criticality in the molten salt reactor is doing by filling the reactor. We put the liquid fuel salt in the core, in the fuel circuits. And then, as I already mentioned, the intermediate fluid is brought to temperature at a temperature higher than the fuel melting temperature. It puts in slow circulation in the intermediate circuit and also in the walls, in the core vessel walls. Then we will fill for the MSFR the fertile blanket at the same temperature. It will be cooled by the intermediate circuits. And then we will inject the fuel salt in the core. And of course, the duration of the filling procedure will have to be reasonable regarding residual power, because as maybe you see on the scheme, the pumps are in the high part of the reactor. It means that when the fuel circuit is not full, you cannot start the pumps, and then you cannot cool the fuel salt. You can cool the fuel salt once the reactor is full. So you cannot take days to fill for the filling procedure. You have to take into account that there is residual power, not for the first time you start the reactor, but for the next times. And then during the core filling, of course, you would like to check if you're not critical before the core is full. So during the core filling, thanks to a neutron source located in the lower reflector, you will inject neutron in the fuel salt and then see the multiplication of the neutron in the salt during the filling with a detector located in the top part of the reactor. And then the idea is to characterize the reactivity at each time of the filling steps, and then to say, well, the reactor will be critical with a volume, with salt volume equal to this, and this being preferably the core volume. And once we complete the filling, the fuel temperature will not be exactly the equivalent to the normal operating temperature, because you can add, I mentioned you can add actinides, you can have many composition, fuel salt composition, so you will have to adjust the composition to reach the correct temperature. This will be done in the next step, step 2, and the power ramp up. It means the divergence step. Power ramp up, once the reactor is full, you can start the pumps, you can start the fuel salt circulation, and then you can also start the circulation of the intermediate fluid, and then you can start cooling the fuel salt. So you will start the fuel circulation, increase the power extraction, and then you will start producing power in the core automatically, thanks to the feedback reaction, which are excellent to stabilize the core. And of course, you will have to adjust the temperature, operation temperature, by adding or removing slowly fissile matter or fertile matter. It means by adjusting the composition of the fuel salt to have the correct normal nominal operating temperature. So next step. So to define to identify some studies we did. Of course, the first time you will start the reactor, there will be a lot of uncertainties on design, on cross-section. So here I present the study done by my colleague Daniel Euer with total Monte Carlo approach on the uncertainty due to cross-sections of lithium, fluoride, uranium-233, and thorium. So it means that the cross-section are known with a given uncertainty, and on the figure on the left part of the slide, you can see a lot of points. So one line corresponds to the filling of the reactor, and if you take one drawn line, a fit, called fit, is correspond to one filling of the reactor, and you have many colors corresponding to many sets of cross-section. We take the cross-section and we modify them to take into account the uncertainty of this cross-section. So you can see that we have a large number of values. So we can, based on the neutron source amplification that you can visualize on the right part, you have a neutron source at the bottom part of the reactor. You can see the filling of the reactor, and during the filling, the neutron multiplication will be modified. You have a detector on the top part of the reactor, and then you can characterize the multiplication impact of the fuel salt, the multiplication factor, in fact, of the fuel salt. And you can also cross this multiplication by the different set of cross-sections to have an idea of the uncertainty on the volume that can be reached when we have uncertainties on the cross section. So it's possible to have the next slide. So the idea is for different volume, you can see that we have a dispersion on the multiplication factor. And on the right part, you can see the neutron flux in the reactor during the filling of the reactor. It's a serpent calculation done by Excel. And you can see that we can estimate the uncertainty of the multiplication factor at the end of the filling. It means that we will do measurement during the filling, and for each volume, we can deduce at which volume the reactor will be critical. And we have a distortion due to the cross-section uncertainties. And if you click, please, we can conclude this. We can adjust the reactivity. We have some levers to adjust the reactivity by, let's say, some hundreds PCM available. So we can either change the fuel salt temperature quickly or slowly. We can modify the composition of what is injected in the reactor. And we can see that since we can modify we can correct the reactivity by 200 PCM, 250 PCM. We aim at predicting the final multiplication factor with a precision we choose of 250 PCM. And we have the precision of 250 PCM when, as you can see on the table in the upper part of the slide, when the fuel salt, when we have 11.5 cubic meter of fuel salt, we have the precision of 250 PCM on the final multiplication factor. It means that when we have half of the fuel salt in the core, it seems okay to have a good precision on the criticality, on the critical volume of the reactor. Of course, here we have to do additional studies because we do not include here internal neutron source in the fuel salt due to neutron production by spontaneous fissions and alpha interaction. And also we have to do similar studies with other nuclear databases. And also we don't need to take into account here the uncertainty due to the cross-section, but there will be a lot of other sources of uncertainties on the first divergence of the first MSR, let's say. So we will have to take into account much more elements on design, on materials, etc., to have a full value, correct value of the full uncertainty on the startup of the reactor. So next slide, please. So to finish, what happens? Okay, we predict. I say that we can predict when the reactor is critical, but let's suppose that we were wrong in our prediction, and then we have the reactor becoming critical before the fuel salt, because the fuel circuit is full. So the core is critical, and we continue adding fuel salt. What if the reactor becomes critical before the end of the filling step, and that we continue the filling step? Of course, the critical temperature will be modified so that the reactivity stays equal to 0. It's the magic. It's the magic of reactivity and of a critical reactor. It's very stable. It means that when it's critical, it stays critical. Only the temperature, operation temperature, that will be modified. But it's not a good thing to do reactivity insertion or in a critical core. So we also have to remind that only the Doppler effect is active at this step. Since the core is not filled, you have not the density effect. You have not an extraction of fuel salt when we have an increase of temperature to the expansion vessel. So you only have half of the feedback effect. So of course, you can modify the composition of the salt injected to avoid the core reaching criticality too early. And of course, the reactor behavior will depend on the filling rates in case of abnormal situation. And of course, it will depend on the criticality volume. But you have on the right an idea of the reactivity insertion when the core is critical and you still add liters of fuel salt. And you can see that we had around 1 PCM per liter that we add in the core once it's critical. So it means that we have an accident of criticality insertion in the reactor at this step. And we have to see what is the effect of fuel injection while criticality is reached. It's a reactivity insertion at low power. And what is the effect of such an accident? So we have to do accidental transient calculations, of course. And then, Axel?
So quite briefly, because it's already 45. So here we have a reactivity insertion when the salt cannot move inside the pump, because we assume that the pump don't have salt inside, so the salt cannot move inside, so there is no natural circulation. So the density effect might be not effective or not completely effective, so we can assume that it's not at all, just to see. And we can see here different reactivity insertions for different times, for different total times, to see what's how important is it. So here we have the margin to prompt criticality. So with the fast insertion, we can see that it's possible to reach here prompt critical state. If the reactivity insertion is slower, it's not prompt critical. We have here the power, which can be very large, with something like a few gigawatts. And here the temperature. What's interesting is that whatever is happening, the temperature bump is not big. The most important thing is the final temperature in the system, and this temperature is only linked to the total reactivity inserted. The second thing is Doppler, is the density effect important or not? So in dashed line we have what's happening if the density effect is working, and you can see here there is there is an impact. But at the end, the only thing which is important is what's the final temperature in the system. And what we can see here in this video is that during this prompt critical situation, so on the right we have the fuel temperature, because of the natural circulation inside the main cavity, the fuel temperature is going to be homogenized spontaneously. So the long-term scale is important, because it's the final temperature, which is linked to the reactivity. But what's going to happen at the very beginning is not that important, which means that finally, if we are critical during the fill-up procedure, it's not that important for the reactor. For the safety, it has to be discussed. So probably for the first reactor, which is going to exist, there will be a control rod to avoid this. But when the reactor will be well known, hopefully, possibly it's not mandatory to have a control rod, because this kind of accident for the safety is not that important. So thank you for your attention.
Okay, it's 3 o'clock, at least in Italy. And we can start again with the interactive module or interactive lecture of this 6th module on MSR operation and control. As I was already mentioning at the beginning of the introductory lecture, this second part will be provided again by CNRS and Politecnico di Milano, and they will be describing in more details the power plant simulator that have been introduced during the first part of this lecture today. So I am introducing again from CNRS Axel Leroux, as well as Hugo Pitois, who is going to provide us this interactive session, and from Politecnico di Milano, Stefano Lorenzi.
So good afternoon, everyone. I will now try to show you how the Liquor code works and how to use it, especially to study transients. So first, I remind you that in order to have access to the code, please send an email to Axel Leroux and Elsa Merle. You will have a download link, and you will receive the code in this zip file, in which you will find first the executable, then the documentation provided with the code, and the input file. So you can, so I will go through the guide first. So as already mentioned, Liquor is a system code. It uses, when it comes to the model, it uses 1D for the hydraulics, and for neutronics, it uses Cos-Bessel functions, and a version of point kinetics that is called the point kinetics per zone. So when it comes to, so the code is written in Java, so it can be executed on every OS, provided that you install Java first, of course. And it can simulate both the core or the core and the intermediate circuit. And as you can see on this picture, it provides a very good approximation in comparison to the Tfm Open Form code that is a reference 3D code used for benchmark. So about the installation, so you will receive, as I mentioned, the zip code. So I suggest you to save this file where you can easily find it. So if you execute it on Windows, you can either launch it using a simple double click, should work. Otherwise, you can use the invite command of Windows. So I will show you briefly how it works. So
you
just
need to have Java installed.
Yeah. I lost audio. You can hear me or can't you?
So good.
Sandra, please, can you check if everyone can hear me?
Seems to be okay.
It's okay.
So if you want to execute it using Windows, you can also use the prompt command. So maybe you have to use it as an administrator. And it will look like this. So once you're in the good folder, the code will start like this. So in this case, you have three scenarios that are already saved as a reference and two standard transients. So in this interface, it will show up like this. So you click on the case you want. So you can either modify the parameters by going through the different categories and click and just modify directly and press enter. I will show you after this. Otherwise, you can directly modify the input file. It will work the same. So this is a way to execute it using Windows, and I will pursue the demonstration using Linux. So it's pretty much the same way. You will use the terminal, and you will just execute it like this. So it's interesting to use the terminal also because it will provide you with extra information when you will start a study.
Possibly some warnings and some help if there are some errors, like impossible input characters, also.
Yes. So here, as you can see, I have already set some different transients that I will go through. Just to continue on the guide. So you will, as you can see, you have quite a lot of parameters. So you have the complete list of all the parameters in the guide in order to modify whatever you need to run the transient. So all those parameters you can find back in here, for example, with regard to neutronics, all that concerns geometry. Especially, you can choose to model the intermediate circuit or not. You can modify the physical chemistry parameters when it comes to the fuel or the intermediate salt, and those two parts are to run the simulations. Yes, Axel, you want to add something?
It's all fine.
Okay. So how does the code present itself? So once you've set your scenario, you will just press this launch and you will arrive on this window. So you have the core, the intermediate circuit, and the emergency draining tank. The code will first start by going through a little step to reach a steady state, and then it will start the transient. So here, this is a reference, so it's just the reactor on the normal operating mode. So you have different information that are provided. You have the temperature, but you can also see different parameters by just clicking. So you have the pressure, the precursors that are decaying. You have the power. So you have different information. You can change the scale by clicking during transient if you are going out of boundaries. I will show you how to do this. And you can run multiple transient in parallel. So in this, I will try to show you how it works to do load following. I first, on this first scenario, so I just change the demand in power. So as you can see, in 100 seconds, I will go from 3 gigawatt to 2 gigawatt, and look how it goes. So you have once again the steady state. So a description of the other info you have. So here is the margin to prompt criticality. So it's as you can see, the reactivity minus the beta effective. You have also, I will just click here, the pump power, the power,
the power for the pump. It says flow rate in the kilogram.
So.
Yeah, but the legend is wrong. I have to change it.
Please do. The precursor decay and the time step. So Liquor uses an adaptive time step. Whenever you ask for a really short transient, especially, it's very useful. So as I mentioned, I asked the power to decrease in 100 seconds. So I just changed the demand in power coming from the third circuit. And as you can see here, so you can have a more detailed view I mean, you can zoom in the different plots. And as you can see, we have the temperature, the delta T in the fuel circuit that is being reduced, as well as an increase on the temperature in the intermediate circuit. And the delta T is also changing. So although you can see that there is no problem and the core is able to follow, this situation is not ideal because we would like to keep the same delta T in the core, especially for the materials, for them not to undergo too much hardship. I mean, issues with temperatures. So we will see how to do this. So as I mentioned before, you can rescale the temperature, for instance, if you want more precise, or it just does not correspond anymore to your situation. So this is a case with when we try load following only by changing the power. Now, if we want to, let's say, keep the delta T in the core constant, what we can do is also modify the flow rate in the core. So in this example, I keep the same transient for the power demand, but I also change the core flow rate. So same idea, going from 3 gigawatts to 2 gigawatts. So I will once again launch the simulation. In the meantime, I can just warn you, you might face sometimes memory issue with Java if it's not set correctly. So I will also show you an easy way to, let's say, try to get rid of this problem. So in this example, you can see that we are changing the core flow rate. So you have this illustration here. And as you can see, here we started to see a decrease in the delta T, but in this case, we can see that we are able to keep the temperature difference. You see there is not much difference. We are able to keep the same delta T, but once again, we will see a difference in the, variation in temperatures in the intermediate circuit. So we were able to do a load following in a good way from the core perspective, but it's still not ideal. So I will show you quickly the last step in order to do a proper load following is by also modifying the intermediate flow rate. So same idea, same variation in a power domain, fuel, and also with the intermediate flow rate type. And here, once the steady state phase is reached, finished, sorry, we will see that if all things go well, that we are able to perform a load following in a very satisfying way. So you will see here that both flow rate inbounds are decreasing in accordance to the scenario we set. And you will see that the temperature should, we should keep the same delta T in temperatures. We might have just a slight increase in temperature in the intermediate circuit because of the transient. There is a delay in the circulation of the fluid inside loops, but otherwise the variation in temperature is reasonable. You can also ask for the plot to have the scales that are set automatically. It's quite convenient. So this is all I want to show you for load following. So of course you can compare at the end the different possibilities, and if you want, you can play back again the simulation by just clicking on the time zone, and you can play it at a higher speed if necessary. Also, so this is a classical load following, let's say. You can also try to see what happened if you have transients that are incidental transient, for instance. So here I present you an increase in reactivity in the core, so 1000 ppm in 100 seconds. So once again, by modifying this, here in the reactivity.
Can you change one value just to explain that? It's important to press enter after modifying a value. That's a command.
I will show you this example, but by modifying directly. So for instance, you choose reference, you can rename the scenario, say, let's say test, because I have lots of imagination. Yeah, you go to transient here, and you set up the reactivity, for instance. So you say I would like a transient starting at 10 seconds, and I would like to go from 0 to 1000 in 100 seconds.
No, in 1 second, something faster.
Something faster? Okay. Let's say 10 seconds or 1000 ppm.
So the important thing is to press enter after putting a value.
Yeah.
If you just write it and you don't press enter, Java don't know it.
And your modification will be noticed also by this turning red. So once the parameters are set correctly, you can start again the simulation. Also, I will show you, but it's possible to stop the simulation by clicking on this button, and so the fuel can go in the emergency draining tank. So here, as you can see, we are putting a lot of reactivity inside the core. So as you can see, we just get out of the boundary, but we can change this. Also here, this value here is the difference in temperature before the emergency draining systems kick in and the fuel is being transferred. But you can do this manually by clicking on this button. So once you do this, you start draining the fuel out, and you will see that the simulations come to an end quickly. So this is for a rather high insertion of reactivity. You can also, I will show you what happens when you have bursts. So it's direct insertion of reactivity. So while the steady state is being reached, I will just show you. Here you have different possibilities. So direct insertion, linear insertion, exponential, or different possibilities. So for the burst here, oh, well, we missed it. I will just run it again. Yeah, I tried to be short, but the code was too fast. As you can see, it's running even higher than one. I mean, it's a real-time code and sometimes even faster. Whenever you are trying to represent a really brutal change, as you can see here, the time step will decrease a lot. And so, of course, the time for the simulation will go longer. So here we can see that by inserting a 100 PCM, so we are not prompt critical yet, but it's quite a large insertion of reactivity. It's, as you can see, almost $1. And so for a moment, we reach almost 11 gigawatts. But as you can see, there is no much variation in the temperature. So even though we face a quite high burst of reactivity, the core can just handle it. So I will, if we have a bit of time, I'll just show a funny last one that I prepared. So it's just to show you that we can somehow badly act toward our core, but it is still capable of handling it without any issue. Of course, you could not try this. I mean, you can do this because you have a liquid core and an excellent intrinsic safety due to the feedbacks. But you could not do this using a standard PWR reactor. So although I think I just asked for too much memory. No, it's okay. So you can see that even though we have quite a lot of variation in power, it's not really a problem for the core. It can handle it. In fact, the core will not be the limiting factor. It will mostly be a problem regarding the structures, because of course, if we are facing a lot of variation in temperatures, the materials won't appreciate. But from a neutronic point of view, it's not a problem. So I think it's all I wanted to present. Axel, maybe you would like to add some things.
That's good.
Okay, now you should see my screen, at least the one with this folder, if you can confirm, because I have two screens and I don't want to mess up the two screens. So are you seeing the folder with the Modelica material, right?
Good.
Okay, Thank you. So in the chat, you can download the material for this section. And actually you will find a zip file with these three folders, MSR folder, thermopower folder, and the simulation results. So in the simulation result, you will find the .mat result of the simulation that we will perform in this section, but the most important, let's say, folder are the MSR and the thermopower. Because as I told you, the Modelica language is based on libraries. So these are the two libraries. So the, let's say, the collection of the component that we use for our power plant simulator. Modelica is the modeling language which is based on which is based our power plant simulator, but then you need some, let's say, program in order to run, to compile, and translate this language. You may have two options usually, let's say the proprietary program or open source program. In our case, as a proprietary one, you can choose Dimola software. And for the open source one, you can find and you can download the Open Modelica software. So I will use the Dimola one because it's more, let's say, fast, let's say, run faster, but you can also use the Open Modelica. So this is the Open Modelica, let's say, environment, and this is the Dimola one. So the first step in order to, let's say, use in general Modelica language is to load the library that you want to use. So let's go here and here. So this is the material in the folder. If we want to load the library on that we developed at Polimi on the molten salt reactor, you just click on package. And here you can find all the, let's say, different let's say, component of this library. In this library, you can see, let's say, for example, the heat exchanger that has been used, or better, the models for the heat exchanger that has been used in the power plant simulator. In this specific case, they are the printed circuit heat exchanger, which is one of the options that could be used in the molten salt fast reactor. And then here you have, let's say, for example, this is the model for the energy conversion system. Up to now, these are not present because we need not only the molten salt reactor library, but also the thermopower library. On one end, the molten salt, the MSR library has been developed by our research group. The thermopower is always developed by Polimi, but in another group. But it's also useful because it's, let's say, it provides us a lot of component for power system and thermal hydraulic system. As you can see here, you have the, let's say, sub folder or sub component for gas. And here you can find all the different components that helps you in modeling system based on gas. So, and here you have, for example, the other one with the water. So since now we have also uploaded the thermopower library, we are able to see the, let's say, the modeling of the energy conversion system. In this specific case, we try to, let's say, to sketch a very preliminary conversion system based on an helium-Brayton cycle. And here you can see the compression stages, then here the turbine one. And so on and so forth. Then you have also the, for example, the fuel circuit. You see that, once again, this mimics the topology of the primary circuit. Here you have the core, then the hot leg, and here you have the heat exchanger. But if you go and let's say open this component you will see that it's, let's say, full of equations that actually represent the behavior of our system. So the structure of this component in terms of, let's say, of the textual, in textual term, it's quite common. You have to declare your variable. You have to declare, for example, here the parameters that you want to use, and then you have the equation part. So here you really type your equation that your component is going to reproduce, is going to, let's say, solve in order to replicate and simulate the component. Just to be very, very simple, let's go back here. For example, this is the Modelica language for a simple resistor, so in which the equation is nothing more than the Ohm equation. And you don't need to specify any input or output relation. You don't have to manipulate your equation. You just write it down, and then it's up to your, let's say, environment to translate the equation into, let's say, real code that will solve this equation. Among that, I want also to point it out one thing that, okay, this is the fuel circuit that we saw before in the demo environment, and for sure one specific peculiarity of our system, of the molten salt reactor, is the drift of delayed neutron precursors, and also the drift of, let's say, the decay transport along the core. So we start from a basic component that was available in the thermopower, which is nothing more than a tube. So it represents the flow, fluid flow inside a tube, and the equation that represents this behavior, it's momentum, mass, and energy balance. And then we add, let's say, the balance for the precursors and also for the decay heat. So you can see and start, let's say, appreciating the fact that since you can rely on a library of components that have been already validated, you can just simply use this component, reuse this component in order to develop your own component. So, and going back here, so this is all the equation related to the part of the thermal hydraulics, and then here we have the implementation of the precursors balance and the decay balance. So we have the fuel salt, then we have also the intermediate loop, and so on and so forth. So in addition, you can also specify the medium that you want to use in your circuit. So you may want to use the properties of the fuel circuit. You may want to use the properties for the intermediate fuel. So this is, I mean, this also, let's say, provides you the flexibility to change the fluid that you want to simulate just by defining the properties of this fluid. Then for sure we have the neutronics part, the point kinetics part. Once again, also here the things are a little bit different with respect to the solid fuel. We have to consider the beta effective, so the fact that since our precursors are circulating, then we have a modification of the effective delayed neutron precursors fraction, and this is considered just, let's say, basically considering the fact that our precursors are moving around our circuit. Okay, then since you can let's say have a look on the different other part, both on the MSR and the thermopower library. What I want to share with you is the full power plant simulator. So we say that we can, let's say, use the different component, we can assemble the different component in order to mimic really the topology of our circuit. And basically, in order to create the power plant simulator, what we have to do is just combine all the different parts. So here we have the primary loop. Once again, it's represented by the, let's say, the physics of the neutral kinetics, the thermal hydraulics of the core, and also the heat exchanger between the fuel salt and the intermediate salt. So here we have really, let's say, a component that mimic the heat exchange between the fuel salt and the intermediate salt. Actually, also this component is made on turn by different component, and this is something. This is just simply the heat exchange between the hot side and the cold side. Going back to the full plant, so then we have the intermediate loop and the power conversion loop. Here you can see some blue and white arrow that represent the input and the output of your system. These are, let's say, some explicit input and explicit output of your system. But if you want to, let's say, perform a simulation on the full plant, I prepare for you. I prepare for you some other simulation. So this is, for example, the simulation of an heat exchanger, in which you have for example, this is the salt coming from the fuel circuit. This is the salt coming from the primary circuit. And if we want to study the heat exchange between them, we can just simulate this component. Okay, let's try to do a first very simple example on this part. So basically, if you have already all the components, you just, let's say, combine them, and you can see, in addition to that, you can see here this line. These are how the different components share the information. Basically, this is the momentum and temperature source of the fuel circuit. And this line share the mass flow rate, the pressure, and the temperature of the fuel salt with the component which is called the primary circuit heat exchanger. Then it's devoted to calculate the heat exchange between the secondary side. And the same here. Here we have the source mass flow rate for the intermediate part. Then we connect with this line these two, let's say, circle, which are the connector. Once again, the connectors share the information between two different components. And then here we have, let's say, the outgoing intermediate mass flow rate that goes, in a sinks, because this is just a simple model trying to, once again, seeing the heat exchange between the primary and the secondary. So in order to simulate this case, we can just simply go to the simulation task. And here you may have all the information that you want to, let's say, input for your simulation: the starting time, the stopping time, the algorithm to solve the your problem. Dimola and in general all the Modelica simulator environment program can use both fixed and adaptive time step schemes. Here you can find the tolerance and so on. So if we start the simulation, so here you can see what actually is doing the Dimola. So basically it takes the code, it translates in C language, we compile the C language, creates an executable and let's say run the simulation. And you can see here from this log that the integration terminated successfully at t equal to 50 seconds. And here we can have access to all the information that are relevant for our system. So we can see, for example, we can have access to the parameter of the heat exchanger, but for example, so we can go on the hot side and we can see the, for example, the temperature distribution. So here, for example, we are going from 1 to 11 because we can decide here which is the number of nodes in which we want to divide our component, our tube actually, because here, as we saw before, we have a tube model. And I mean, on the top of that, here you can see that you can just input all the parameters that you want. You can change all the parameters that you want. So going back to the result, so here we have, since we have discretized our, let's say, our heat exchanger in 11 nodes, we can have the distribution of the temperature inside the heat exchanger in these 11 nodes. You can see here that we are going from 741 Celsius degree until the last one, which is 640 degree. So we have a delta T of 100, which is usually taken as a reference for the molten salt fast reactor. For sure, this is not the only information that you can retrieve. I mean, you have access to all the, let's say, variable and parameter that have been used for the let's say for the creation and for the modeling of your system. Then, if we go back to the fuel plant simulator, then we can do the same thing here. Run, and also here we'll see that so we have to, let's say, give some time to Demola to compile and to run the simulation, but it's, I mean, pretty fast, also compared to the let's say, the time scale. So usually this kind of simulator requires to spend a quite remarkable, let's say, simulation time, and they have to be, let's say, fast running in order to perform this this task. So we are more or less done. So in the meanwhile, especially the Demola program, it's quite good to also to initialize your problem. So to find which is the, let's say, steady state of your problem, of your let's say, of your simulation, starting from different parameters. And here we have the result. So also here we have the so this is just simple a simulation that start at power 3 gigawatt. Then we have the core temperature. These are in Kelvin, but we can switch quite easily to Celsius degree. And we find, once again, more or less the same value that we have found in the case of just when we have just the heat exchanger. Then you can find the intermediate, so the minimum temperature in the intermediate circuit and the maximum one, and then the temperature of the gas, so at the beginning and at the end of the heat exchanger. So for example, this temperature. So here you have the helium gas that enter the heat exchanger and the exchange power with the intermediate one from cold to hot. And you can have also this kind of information. And then you can also have a first estimation of the mechanical power that we can extract from our system. Obviously, in this case, we are considering just a very simple case, so it's not taken as a reference one, but provides you the idea that about the potentiality of this simulator. So, as you can see, I mean, here, once again, so let's do this way. Then here you can find all the subcomponent, all the information related to the subcomponent. Among these, you can find also the core average temperature. And for example, we can see that in this case, the average temperature is at 691. So, and also shown by Hugo and Axel, if we want to increase the temperature, if we want to vary the temperature, we need to change, for example, the reactivity. So, how to change the reactivity in this case? So, we have here the this is transient, so this is an input block that provides you the kind of transient that you want to provide to your input. So let's say that we want to provide 30 PCM starting from 100 and with a duration of 60 seconds. And okay, let's try to simulate this and we provide, let's say, 500 seconds as final stop time and see what happened. So now we'll perform a transient in which we are providing 30 PCM of reactivity in 60 seconds. What we are going to expect is that our temperature will increase because of the reactivity feedback that trying to counterbalance this external reactivity. And since we are inserting positive reactivity, we want negative reactivity, and since MSFR has strongly negative reactivity, we'll end up with an increase of the average temperature. So let's see what happens here. It's initializing the model. And by the way, I mean, here, once again, you have plenty of information with respect to the primary loop, the intermediate loop, and all the other components that that represent your model. So let's go back here. So once again, let's switch to the Celsius degree, and here we go. So as you can see, the average fuel temperature has increased by, let's say, almost say 8 Celsius degree. You can easily, let's say, calculate this variation by hand, because if you know the reactivity coefficient, you can also calculate this part. And here you can see the, let's say, the power variation in terms of the core. This is a quite, let's say, quite smooth one. Then you have, you can see the variation of the decay power, here you can see the different composition of the total reactivity, in which you have the part related to the positive and the negative one, and so on and so forth. I want just to show you the very last simulation. For sure, when we talk about, when you say that if we want to change the power of the reactor, what we are going to do is changing the heat extraction. In this case, this can be done by varying, for example, the mass flow rate by, let's say, 10%, an increase of the 10% of the mass flow rate of the convection system. In this case, it's the helium. So let's try to see what happens. So here in this case, so I don't know if Sandra, in the meanwhile, I can answer some questions.
Okay, thank you, Stefano, for your presentation. I actually, at the moment, there are no questions from the audience, so I interpret that also to the fact that the presentation of the simulator, of course, becomes extremely useful in the logic of giving the opportunity to the participant to the school to test them, to use them, let's say, to play around with them, if you allow me the expression. So I really strongly suggest to the participant of the school to actually use the channels for the download of the material that I was posting on the chat, the WeTransfer link for what regards the Modelica simulator, and the email address in order to ask for the CNRS simulator, so that you can actually try to use it. This could also become a nice subject for a capstone project that will be offered, will be proposed at the end of this school, so in December. I will therefore, since there is no specific question asked, I will.
Yes, sorry, Sandra. I will just. Yeah, sorry. We'll just show the result of this simulation. So.
Cool.
By increasing the mass flow rate of the energy conversion system, we are increasing the mechanical power, but also the power in the reactor. And as you may want, you can see. So since we are not touching, let's say, the neutronics of the system, we can see that the average core temperature start from a certain value as this, let's say, undershoot, but then it will establish to exactly the same value of the first, let's say, of the beginning of the simulation.